This is the IBM Capstone project for 2017. Our goal in this project was to use machine learning to predict Jenkins scores of OpenStack projects. In addition, we also had the side goal of using object storage, in our case S3, to share the machine learning model easily between data researchers. For machine learning, we used TensorFlow, a machine learning framework by Google. It's based on the idea of data flow graphs. Nodes in the graph represent operations, while the graph edges represent data arrays that flow between them. This web page is the web interface for the OpenStack Gerrit instance. You can see here these are all changes for various projects inside the OpenStack ecosystem. We'll click on one here and just take a look at what an individual change looks like in OpenStack and inside of Gerrit. The key piece of information we're using for our machine learning purposes, amongst other things, is this verified tag by Jenkins. This +1 means Jenkins has verified this change works and is valid, and it passes all the tests that Jenkins runs. We also use other information, other metadata in each change to help in our predictions, and this is part of our data set. So we use things like the author, the project that this particular change falls under. We also track lines of code changed and removed and added. In addition, we use a few other, we've tried out a few other data set points that we thought would be useful, but we won't cover those here today. The first step that I'm going to show in our project is the data collector. This is how we get our initial data set that we can pass into our TensorFlow model. This data set contains, obviously, whether or not the change passed, as well as all the heading items you see here on line 1. So this CSV is generated by a collector utility that we've written, and that allows us to push this data into TensorFlow. The next step we'll show off is the generation of the model itself. This is all written in Python, and we're using, again, TensorFlow to build our model for us. Some key standout points here I'd like to make. This is essentially just some output. We're running 10 iterations of TensorFlow, and the most important value here is each training step's accuracy. So here we're getting about 60% of the time we're guessing correctly, essentially. And we've added this last input line here to allow you to save the model to a file, as well as the project ID mapping, which we won't get into, but essentially TensorFlow requires all data points to be numbers, and since the project name is a string, it's the name of the project, we need to do that conversion, and we need to also track that conversion so other users know which IDs map to which project names. So we'll go ahead and save this model because we like this percentage, 60%, not too bad. So you can see here we save off our model, we save that mapping file I talked about, and lastly we upload all of that information to S3. The idea being that someone doesn't have, in order to use this product, someone doesn't have to actually generate the model. Instead, they can choose to just run our live component, which I'll show next. So the person that's consuming this product doesn't have to know anything about machine learning. They can automatically pull down all the files they need, and they can run the live component, which is the next bit I'll show. So again, Python, just a simple Python command. This will download the model and everything it needs from S3, and then it'll go ahead and start monitoring Gerrit events. We get a ping through the Gerrit API, the OpenStack Gerrit API, that every time there's a change in the system, we get a result back, and we'll do a guess on whether or not there is every time we guess there's a change, whether it will fail or succeed. So in this case here, I'll stop it right here and just show off a few features. So we have 3 events that came in. There's a lot of commits that are being done to the OpenStack in the OpenStack project group. We're basically each time guessing this test is what our test score is for these particular values. So this is a particular change, and we're guessing that just below 50%. So in general, we think this particular change will fail. And in some cases, we already actually know the Jenkins score, like I showed earlier in the web UI, and so the actual score we also list. So in this case, we did get it right, just below 50%, and it was a failing change. There's a couple other cases here where we guessed it correctly, and then this last one, we didn't actually have a project ID mapping, and so we couldn't actually run the tests because we didn't have that mapping done in our original model. So all this put together is sort of our project. It's sort of three different pieces kind of put together, the S3 component as well. And so the idea being going forward that someone could take this work and improve on the model or start to look elsewhere and do more analytic work on trying to determine whether a particular commit will pass or fail. So you can see maybe coding style, different other data points that are available to us in the metadata. There's a lot of possibilities here, but again, this is just a proof of concept of where we could go as far as trying to predict Jenkins score and saving time and money as far as the Jenkins builds taking a while to run.